Hello everyone. In this lecture we shall discuss the solution of nonlinear programming problems by using dynamic programming technique. Okay, if you recall the previous lecture where we have solved the LPP linear programming problem by using DP technique. So here we solve the NLPP. You see this example. Here the objective function is non-linear. Okay, and you see the second problem. Here the objective function is non-linear, right? There are three decision variables, and we can also simultaneously extend it to n decision variables, right? So in my second part I will discuss that type of problems where we need the use of the induction. So here we shall discuss two problems. Problem number 1, use dynamic programming technique to solve minimization of z is y1 square plus y2 square plus y3 square subject to y1 plus y2 plus y3 greater than is equal to 15 and y1 y2 y3 non-negative. And the second problem, maximize your y1 y2 y3 product subject to the constraints y1 plus y2 plus y3 is equal to 5 and y1 y2 y3 is non-negative as usual, as per the usual practice. Okay, so now coming to the solution of solution of problem number 1, right? So there are three decision variables, so it is a three stage problem, right? Since there are three decision variables, so it is a three stage problem with state variables say S1, S2 and S3 as defined as follows, right? As follows. What is your S1? S1 is, here you say this y1 plus y2 plus y3, y1 plus y2 plus y3, right? And as per practice, as given, it is here greater than is equal to 15. Now what is my S2? S2 is equal to y1 plus y2, right? So that is equal to, I can write S1 minus y3. Suppose I take this is your S3. Okay, so this will be my S3 minus y3, and what is my S1? S1 is equal to y1 only. So this y1 is here S2 minus y2, okay. Now we'll write the recursive relation and proceed to solve. And before that, let me to introduce myself, Professor S.K. Paikray, Kumar Paikray, currently working as a Professor of Mathematics at VSUT, Veer Surendra Sai University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to write the recurrence relation, and consequently I will solve the three stages. Okay, and here we use the calculus for maximization and minimization. Suppose you are given a function y is equal to fx. How to find the maxima minima, right? You need to find your f dash x is equal to 0 first. Then you find the value of x. You say suppose it is x0. It is your stationary point now, right? Now at x0, or you may have one or more other values also. So now at this point I have to check the second derivative, right? Second derivative at the point I have to check. If it is negative, then it leads to maxima. If it is positive, then it leads to minima. So we should work on this principle. Okay, we will work on this principle. So let me to write the recurrence relation, and we use this technique simply to get it solved. Okay, so without much delay, let us solve the details. Let this be my stage 3, this is my stage 2, and this is my stage 1. Okay, thus the functional thus the recurrence or functional relations are here f1 s1 is equal to, we start from this, so this is my minimization of y1 square, right? Minimization of y1 square, right? So this is equal to here s2 minimization of, here y1 is s2 minus y2, s2 minus y2 square, right? Here the range of s1 will be, range of y1 will be, minimum it is 0, y1, and maximum it is s1, right? It is s1. So now let it be a equation 1. Now what is f2 s2? Here f2 s2, right? It involves 2. We'll take 2 variables here, y1 plus y1 square plus y2 square. We'll take f2 s2 is equal to minimization of y1 square plus y2 square, y1 square plus y2 square, right? So y2 varies in the range, we'll write. So this is equal to minimization of, I will write y2 square, and for y1 square, right? For y1 square I use the previous one, okay? Plus it is f1 s1, plus it is f1 s1, right? And what is the range here? The range of, so here it is here y2, so y2 is here 0 less than equal to y2 less than is equal to here s2. So this should be the range. Let it be here equation number 2. This is equation 1, this is equation 2. Then we write f3 s3. f3 s3 means it is minimization of, right, y3 square plus y1 square plus y2 square, y1 square plus y2 square. I write first y3, or you write in order, no problem. So this is equal to here minimization of, so regarding this 2, okay, we use it here, right? So this is minimization of y3 square plus, and this is nothing but f2 s2, right? f2 s2, this is your f2 s2. So now let it be your equation 3, and here the variable is y3. So y3 having the range, it is 0 less than y3 less than s3. Let it be equation 3. So these are the recurrence of the functional relations, okay? Now we start solving these relations. Let us start with this f2 s2, okay? Now from equation 2, my f2 s2 is equal to minimization over y2, it is y2 square plus f1 s1, right, plus f1 s1. So I write it minimization over y2, here y2 square is y2 square, but f1 s1 is my y1 square is my s2 minus y2 square plus s2 minus y2 square whole square, okay? Now just I open it, minimization over y2, I just open this a minus b whole square. This is s2 square plus s2 square minus 2s2 y2 plus y2 square. So this is equal to minimization of here 2y2 square plus s2 square minus 2s2 y2. So let I say this is a function. Suppose I say this function is my u say. So this is equal to minimization of u say, right? Where u is equal to, here u is equal to 2y2 square plus s2 square minus 2s2 y2, okay? So now I want to solve y2 in terms of your s2. So now I use this principle here. First derivative 0, okay, and second derivative is it is a minimization problem, so positive, right? Positive, we have to work on this principle. Okay, so now what is your du by dy, right? Du by dy2, so this is equal to 4y2 plus, so this implies this 4y2 and this is your 0 minus s2 is constant to 2s2. Okay, so this is equal to, I can write it 0 because the first order condition, first derivative is 0, okay. So this implies, we solve it, what is your y2, so this implies your y2 is equal to s2 by 2. So we get the value of y2 in terms of the state variable s2. Now to ensure that it is a minimization problem, we have to find the second derivative, right? What is my second derivative? So my d square y by dy square, so this is 4 and it is 0, so it is 4 is positive, so it leads to minimization, right? It leads to minimization. So the minimization of f2s2 is attained at y2 is equal to this. This minimization is attained at y2 is equal to this. So now what is this minimized value, right? The minimized value of f2s2 is this, I substitute here. So f2s2 is equal to thus here f2s2 is equal to here y2 square plus s2 minus y2 whole square, right? y2 square plus s2 minus y2 whole square, that is equal to, I can write y2 is my s2 by 2, so it is s2 square by 4 plus here s2 minus s2 by 2 whole square, right? So this is 2s2 square by 4, this is your s2 square by 2. So therefore what I am getting, so that means my f2s2, right, my minimized f2s2 is what I am getting, s2 square by 2, right? s2 square by 2. Now we move to equation number 3. So here this is because of the second order condition, second derivative is positive or negative. Okay, now consider your equation 3. Now from equation 3 here f3s3, what is f3s3? It is minimization over y3, right? It is your y3 square plus f2s2, this is your equation number 3, right? Plus f2s2 and minimized f2s2, we get it, so we write it. So this is minimization over y3, it is y3 square is y3 square plus half s2 square, this value plus half s2 square. Now what is s2 square? So this is equal to minimization over y3. Okay, so this is y3 square plus half, what is your s2? Your s2 is, you see, s2 is s3 minus y3, s3 minus y3 whole square, okay, whole square, right? So let it be my v. So this will be my minimization over y3. I can split it, y3 square plus half s3 square plus y3 square minus 2 s3 y3. So this is equal to, I can add it. So this is minimization over y3. So this will be 3 by 2 y3 square plus 1 by 2 s3 square minus s3 y3. Okay, let I call it my v. So this is equal to, you say, minimization of v, right? Some function v, where here v is equal to 3 by 2 y3 square plus half s3 square minus s3 y3. Okay, so now find the first derivative, dv by dy3. So this is equal to derivative of this is 3y3 plus 0 minus here s3. Okay, this is equal to 0. It is because of the first order condition. So that means what is your y3? y3 is equal to your s3 by 3. So the minimum value attained at s3 by 3. So now to confirm, so this implies my d square v by dy3 square. Okay, so this is equal to 3 and this is your 0. It is 3, which is positive. So it leads to your minimization. This minimization is because of your second order condition. Second derivative is positive, then it is minimization. Now we need to find the minimized value of your f3s3. Thus, what is my f3s3? My f3s3 is equal to your y3 square plus half s3 minus y3 square. Isn't it? So what we are getting, I am substituting the value of y3 here, right? The value of y3 is substituted here. So this is equal to here y3 is s3 by 3 whole square plus half here s3 minus s3 by 3 whole square, right? So this is equal to s3 square by 9 plus half, it is 3s3 minus s3, the 4s3 square by 9. Okay, if you simplify it, so this is 2 and 4 cancelled, so it is 3s3 square by 9. So this is s3 square by 9. So what you are getting, f3s3 is your s3 square by 9. Okay. Moreover, as per the given condition, here y1 plus y2 plus y3 is greater than is equal to 15. So y1 plus y2 plus y3 is s3. s3 is greater than equal to 15. So minimum value of s3 is 15. Okay. Moreover, I write moreover s3 is equal to y1 plus y2 plus y3 is greater than is equal to 15. What does it mean? It means minimum value of s3, right? It's greater than equal to 15. So minimum value of s3 is here 15, right? So since we are looking at the minimum value, so thus my s3 is equal to 15. If s3 is equal to 15, so what is my y3? y3 is s3 by 3. So this is equal to 5. Now we are ready to find s2. What is your s2? s2 is s3 minus y3, isn't it? So what is your s2? You see, s2 is s3 minus y3. So I write it s3, my 15 minus y3 is 5 is equal to your 10. So what implies your y2? Right, y2 is your s2 by 2. This is equal to your 5. Clear? So this is your s2. Then what is my s1? s1 is s2 minus y2. So s2 is your 10. So this is equal to this y2 is equal to 1. So this s1 is s2 minus y2. s2 is your 10 minus y2 we are getting 5 is equal to 5. So therefore here s1 is equal to y1. s1 is equal to y1 is equal to here 5. Okay, so what we are getting, y1 5, y2 5 and y3 5, right? So clearly minimization of z, minimized z attains at y1 is equal to y2 is equal to y3 is equal to 5 with minimized value, with minimized value of z is equal to how much? Here y1 square plus y2 square plus y3 square is 25 plus 25 plus 25 is equal to 75. Okay, hence the optimal policy is, hence the optimal policy is here y1 is equal to y2 is equal to y3 is equal to 5 with minimize z is equal to 75. Okay, so this is your answer. So now coming to the solution of 2. Question number 2. Similarly, it is a 3-stage problem, right? It is a 3-stage problem. It is a 3-stage problem with state variables S1, S2 and S3 defined as follows. Okay, so let my here S3, we start from S3. Here S3 is equal to y1 plus y2 plus y3 is equal to 5, right? This is 5 given. So now here S2 is equal to, you take y1 plus y2, right? So this is equal to here S3 minus y3, and my what is here S1? Here S1 is equal to y1. So this y1 is equal to here S2 minus y2. Let it my stage 3. It is my stage 2. It is my stage 1. Okay. So now we write the recurrence relation. Thus, the recursive equations are F1S1 is equal to here y1 is equal to maximize y1. So F1S1 is equal to here maximize y1. Okay, maximize y1. So y1 ranges our, right, maximum is S1, y1 is equal to S1 and minimum non-negative value. So that is equal to, I can write maximization over y1. Okay, and this y1 is S2 minus y2, right? Y1 is my S2 minus y2. Let it be my equation 1. Then what is my F2S2? It is maximize over y2, right? And here I take it here y1 y2 or y2 y1. So I write it, this is equal to y2 y1, y2 into y1. Now this y2 is y2, because the variable we are taking here is y2, 0 less than y2 less than here s2, and this y1 value will be substituted here, right? So this is equal to maximization over y2, it is y2, and this value is here f1s1. Okay, this value is here f1s1. So let it be your equation number 2. Now what is your f3s3? F3s3 is equal to this maximization over y3, it is y3 y2 y1, right? And this ranges from S3 ranges from this, so that is equal to, you can write it maximization over y3 remains silent, and for the value of y1 y2 we substitute this. Okay, we substitute this. Sorry, this is y2 na, this is y2, so this is already y2 silent, so this value I am substituting here, y2, this is my f2s2 I am substituting. Okay, so this is y1 y2 is my f2s2. Okay, so now let it be my equation 3, right? Now I solve the state variables and the decision variables by solving these 3. I start with equation 2. Consider equation 2. Okay, from equation 2, we have here F2S2 is equal to maximization of, here it is maximization over y2, right, y2 plus f1s1, and the value of f1s1 is, I substitute maximization over y2, it is into it is y1 into f1s1 is, it is y2, it is s2 minus y2, right, it is s2 minus y2. So this is equal to maximization of s2y2 minus y2 square, s2y2 minus y2 square, right, it is over y2. So I write it, suppose I write it maximization over y2, I write it u say, here u is equal to s2y2 minus y2 square. Likewise in the previous step I find the maximized value. So this implies my du by dy2 is my s2 minus 2y2, and this is equal to 0 because of the first order condition, first derivative is equal to 0. So this implies what is your y2? y2 is equal to your s2 by 2. So with this value, what is my f2s2 now, minimized value of f2s2? So this implies my f2s2 is equal to here y2 into s2 minus y2. So this is equal to s2 by 2 into s2 by 2, s2 minus s2 by 2. So this is equal to s2 by 2 into s2 by 2. So this is equal to s2 square by 4, right. So what I am getting, so my f2s2 is s2 square by 4. Now we move to equation 3. From equation 3 we have one more thing, we get y2, but we have to ensure that it is a maximization, okay. So this implies we differentiate it here, okay, differentiating what is here, d square u by dy2 square. So this is my minus 2, it is negative, so negative means it leads to maximization. This maximization is because of the second order condition, okay. So this maximization is guaranteed. So what is my maximized value? Now the maximized value is this, okay. So my maximized value is this, the maximized value, I need the maximized value, so this maximized value is this. So next from equation 3 we have what is your f3s3, f3s3 is equal to maximization over y3, it is y3 into f2s2. Now the value of f2s2 is this, okay. So this is equal to maximization over y3, it is y3 into 1 by 4 s2 square. Now the value of s2, you know, it is s3 minus y3. So this is equal to maximization over y3, it is y3 into 1 by 4 s3 minus your y2 square. Sorry, this is y3, s3 minus y3 square. So now I simplify it. So this is equal to maximize over y3, it is 1 by 4, okay, 1 by 4 y3 into, this is your s3 square minus 2 s3 y3 plus y3 square, okay, plus y3 square. So that is equal to, I can write maximization over y3 1 by 4, this is s3 y3 square minus 2 s3 y3 square. So this is equal to maximized, it is here 1 by 4 y3 s3 square minus 2 s3 y3 square plus y3 cube, okay, plus y3 cube. So let I say this is my v, I say this is my v. So this is equal to maximization over y3 v say, where my v is equal to 1 by 4 y3 s3 square minus 2 s3 y3 plus y3 square. So I apply the first derivative here, first derivative is equal to 0. So this implies my dv by dy3 is equal to 1 by 4 s3 square minus 2s3 plus this is q, y3 q. So this is 3 y3 square. This is equal to 0 because of the first order condition, right? First order condition. So this implies, if you simplify it, implies here 3y3 square minus 2s3 plus s3 square is equal to 0. Now one rectification, it is s3 y3 square. Okay, so it becomes here 4. It becomes here 4 s3 y3. So it becomes here 4 s3 y3, right? s3 y3. So we solve it. So we apply the middle term factorization here, right? This is 3, this is 1. So 3 into 1 is 4. We want to make it 4. Okay, so 2 into 2. Or we want to make it, it is 3. So minus 3 minus 4 plus, so it is at 3. So minus 3 minus 1. Okay, so 3y3 square minus 3s3y3 minus s3y3 plus s3 square is equal to 0. So that means here 3y3 taken common, it is y3 minus s3 minus here s3 taken common, y3 minus s3 is equal to 0. Okay, by middle term factorization. So what we are getting? We are getting here y3 minus s3 into 3y3 minus s3 is equal to 0. So that means y3 is equal to s3 or y3 is equal to s3 by 3. Okay, two values we are getting. So now we have to ensure the maximum. So what is my second order condition? My second order condition. Okay, here d square b by d y3 square is equal to. So now we differentiate this twice. Okay, so differentiate this twice. This is 0, and so this will be my 1 by 4 6y3 minus 4s3, right? 6y3 minus 4s3. So now we check at this point and this point. Okay, so d square v by dy3 square at here y3 is equal to s3. What I am getting? So it is 1 by 4 here 6y3 minus 4y3. So y3 is non-negative, so this is positive. It is greater than equal to 0, right? Greater than is equal to 0 means minima, but here we are talking about maxima, right? So this is neglected. So now d square v by dy3 square at here y3 is equal to s3 by 3. Okay, what is the value we are getting? So this will be equal to 1 by 4, it is 2s3 minus, it is 2s3 minus 4s3. Okay, so this is equal to, we are getting minus 2s3 by 2, which is negative because s3 is positive. Right? So this is less than 0. So the less than 0 means it leads to a maxima. So this value is accepted, right? Thus out of these two values, okay, this value is accepted and this value is rejected, right? Because it will not give you the maxima. And one more thing, it will strictly greater than 0. So now what we are getting? Thus taking y3 is equal to s3 by 3, 1 by 3 s3, we have what is your s3? S3 is equal to y1 plus y2 plus y3 is equal to 5. So this implies what is y3? Y3 is s3 by 3. So this is equal to 5 by 3. So the value of y3 is my 5 by 3. Then I come to your s2. What is s2? S2 is equal to your y1 plus y2. So that is equal to s3 minus y3. So s3 is 5. 5 minus y3 is 5 by 3. So this is equal to 10 by 3. 10 by 3. So this implies what is here y2? y2 is equal to s2 by 2, as we have seen earlier. y2 is equal to s2 by 2. We have seen here y2 is equal to s2 by 2. So this is equal to here 5 by 3. 5 by 3. So the value of y2 is also 5 by 3. So then what happens to my s1? s1 is equal to y1 is equal to here s2 minus y2. What is here s2? s2 is here 10 by 3. Right, it is here 10 by 3 minus 5 by 3. So this is equal to 5 by 3. So this implies what is here y1? y1 is equal to 5 by 3. So we are getting y1 5 by 3, y2 5 by 3 and y3 5 by 3. Hence the optimal solution is Z max is equal to 5 by 3 into 5 by 3 into 5 by 3. This 125 by 27 at y1 is equal to y2 is equal to y3 is equal to 5 by 3. So this is your answer. Okay. So we should close this lecture here. So this is the optimal solution. Now at this stage we can conclude like this. You know, the nonlinear programming problem has different approach to solve. For equality constant we have Lagrange multiplier. For inequality, not equality, if all the constants are not of equality sign, then you use Kuntukar condition. Yet this dynamic programming problem also, DP technique also help to solve the NLPP as we did it in this way. Now if there are, in upcoming lecture we'll see if there are n decision variables, then that means you say suppose minimize z is equal to your summation of pi log pi, right? I is equal to 1 to n, means there are n decision variables p1, p2, pn, right? And subject to the constants, you say subject to the constant summation of pi is equal to 1, means p1 plus p2 plus pn is equal to 1 and pi greater than is equal to 0, right, for all I equal to 1 to n. So this type of problems, okay, with n decision variables, you can see any standard reference book to solve the problems involving n decision variables. Okay. Also in my part 2 lecture I will discuss this type of problems. Okay. So at this stage my appeal to you, if you feel this lecture is useful and interesting, please like and subscribe to my channel, which will boost my motivation to upload subsequent lectures for your benefits. So let us close this lecture here. Thank you all. Have a nice day.